Thank you very, very much for being here.
Thank you for the invitation, and I'm really sorry that I'm not there with you today, but COVID has visited us, the full family, so I thought it was safer to stay at home. Anyway, I will try to give my presentation, and please, if you have any questions, please feel free to ask me or even send me an email. I have my contact details there. So can you all hear me? Can you see the screen?
We can hear you and we can see the screen.
Great.
Yes. So you may start.
Okay, so I'm now starting. So I will be moving a little bit the focus of the talk. So I will be moving away from the policy side that previous colleagues gave us today, and I will be moving to more technical stuff, and we'll be discussing how we could somehow try to start estimating both those fluxes of carbon and storage in forest ecosystems. And actually, some of the slides and the methods that I will be discussing today could potentially be applied, especially in agroforest systems. So we have also tried to do that so whatever you see today, imagine that theoretically it can be transferred to agroforest ecosystems. And we have tried to do that for the olive grove of Lesbos, but unfortunately, I will not be showing these results today. And I will be mainly concentrating on forest ecosystems. So my name is Nikos Fyllas, and I'm working at the Department of Biology in the University of Athens. And this is work that we have been doing with these two PhD students of mine, Chris Sazeidis and Eva Binci. And let's see how we can see that. So before going into the details of how we could estimate these carbon fluxes, I would just like to give maybe a reminder for those of you that have not seen these figures or this analysis in the past, is how we actually Earth system scientists realized or actually proved that carbon in forest and actually its dynamics are quite important for the whole planet. So until, let's say, the end of the previous century, our French climatologists were considering, when they were running the 3D global circulation models to predict how climate might change given some emission pathways, they were considering vegetation to be stable. So just to provide across the globe a constant layer that it was absorbing carbon, whatever the climate or the disturbances or whatever the environmental conditions were. But back in 2003 and 2004, Peter Cox and his colleagues presented the first actually pivotal Earth system model where they changed vegetation from a completely stable behavior to a more dynamic approach. And this gave some quite interesting results because following climate change, it ended up saying to us that because, of course, as ecologists, we know that vegetation responds to the environmental conditions that is under. If following a business as usual scenario with high concentration pathways and quite high increases in temperature, this could end up in vegetation in many places, stopping to provide a sink, so absorbing carbon dioxide from the atmosphere, and actually providing a source of carbon. And this would accelerate global warming by the end of this century. So it was an estimation that about a fifth more of that CO2 concentration would be about a fifth more of 20% more of what was estimated if we ignored these feedbacks from vegetation. And actually, this was mainly happening in these simulations because the Amazon forest died or died off, and because many places, and actually the soil carbon in many places, started to respond to higher temperatures and being respired in the atmosphere. So this is just to keep that in mind that, these things that we are discussing are also important from a global perspective, and we need to try, or at least try to see them in a dynamic way. So if we go back to the basics of ecosystem and ecology science, what we more or less know is that we have those carbon fluxes which are linked with energy fluxes, and actually forests and many ecosystems absorb carbon dioxide and from the atmosphere, and they are transforming it to biomass through the process of photosynthesis. This carbon is then accumulated in either in the form of biomass, dead wood, litter, or transferred to the forest soils. We can also have releases of carbon from these ecosystems, which could be either due to natural processes like respiration, or deliberate or unintended human activities like harvesting or fires or deforestation. And actually, the pathway of this flow can be nicely given in this graph. So essentially, we start off with gross primary productivity. You might see that as GPP, which is actually the total amount of carbon that is fixed through the process of photosynthesis by plants. And then an amount of this carbon is being used through by autotrophic respiration to support, how plants work, and this is released to the atmosphere. So then we are talking about the net primary productivity, which you might see it as NPP. And then another amount of this carbon is emitted to the atmosphere because of the decomposition of dead organic material, and this is called heterotrophic respiration. So the next variable, or the next element that we would like to keep in mind, is the net ecosystem productivity, NEP. So most of the carbon farming business would actually look after or try to find this number. So how much carbon per unit of area and per unit of time is being stored in an ecosystem, which actually it might be even better to go to the next variable, which is the net biome productivity, which is in the longer term. If you also take into account harvests, forest clearance, fires, or other sort of disturbances, you need to exclude those carbon released from this process as well. But mainly, we will be talking about this net ecosystem productivity, this NEP, today. So how can we estimate those storages, those carbon storages, and those fluxes? Well, there are different methods. I think I am mentioning, and I will be discussing the key or the most important of those methods. Maybe there are others, but I think the key ones are here. So these are the inventory-based methods, the satellite-based methods, the process-based methods through models. Only for fluxes, there are also the eddy flux tower approach. And of course, there are fused methods of all the above, especially when we want to upscale from very local measurements to the regional or to the landscape level. So let's go through those approaches. And actually, I will be showing today, I will try to be quite practical, and I will be showing today the way that we have tried to use those approaches, or the way we have applied those approaches in the forest ecosystem across the island of Lesbos. So these inventory-based methods, what we more or less want to do is to keep track of the carbon, of the growth, of the decomposition, of any other fluxes that are happening in a small parcel of land, especially in forests. These are the most traditionally and probably the most accurate methods that we can find, but they are quite costly, and they are time consuming because they are based on field measurements in generally permanent plots. So plots that we are monitoring what is happening in a permanent way. Usually what we do here is that we are trying to estimate the biomass. Usually it's above ground, because below ground biomass in most of the cases it's quite difficult to get, of individual trees. And we want to relate those quantities with other biometric variables that are easily measured. For example, the diameter, the height of the tree, and things like that. So in this way, we are creating these so-called allometric equations, where we can easily measure some characteristics of the trees. And from those, we can in generally accurately estimate their biomass. And of course, if we are in a parcel of land, in a plot area, if we add up all these different biomasses of the separate trees, then we end up at the biomass of the plot. And a portion of this, usually it's considered about 50%, is how much carbon we have there. So the images that you see here is from one of the plots that we are maintaining, and I will be talking about that in a while, that we are maintaining on the island of Lesbos. If I'm not wrong, this is a Pinus nigra plot. And here you can also see other sort of measurements that we are doing in these permanent plots, where we're gathering the litter, or we're estimating the fluxes from the soil using more advanced techniques. So once you have these allometric equations, as I told you before, you can more or less try to estimate how much biomass you have through different methods. I will not get into detail of what these symbols are, but basically you measure an easily measured variable, and then you use this variable to estimate the biomass of each one of the trees that you have in your plot. And once you have 2 points in time, then of course the difference would be how much, what is the rate actually of your carbon either increasing or decreasing. In generally, what is the rate of your biomass changing, and what does this mean for the carbon in this very specific area. So some quite practical things. What we have been doing is that across the island of Lesbos, you can see these points here. This is the permanent forest plot network that the University of the Aegean is maintaining there. And actually, it's almost 5 years now that we have set up all those plots, and we are monitoring every year, actually every 3 months, what is happening to the biomass within those plots. And these plots have been set up across a post-fire chronosequence, so actually across different time seasons, the last big stand replacing fire. And we are doing that to mimic what are the effects of stand structure. So how the stand structure changes, what would this mean for the total biomass and the fluxes within the plot. And we also have set some of those plots across an elevation gradient, ranging from 350 to 750 meters, where actually there we're trying to see what are the effects of microenvironmental conditions on the sea fluxes. So this is our plot. Currently, it's our plot network. Currently, we have 15 plots measured quite frequently. And these are the very first results of these methods. So what we did is that we expressed the total biomass, we estimated the total biomass of the plots, and then in 2 different points in time from 2019 to 2022, we estimated how much each tree has increased in biomass. So if you do that, and here more or less you see this post-fire chronosequence plot, so it's 15 years after the last fire, 45 years, about 70 years and 90 years, you can nicely see, this sort of dynamics and how trees are growing and how this can be translated to carbon. But in this approach, we don't only count how much trees are increasing, but we are also counting how many trees and what was the size of the trees that died. So we also have, what we are losing in terms of biomass and carbon. And if we do these calculations, we more or less end up with results like this, saying, that in the younger plots, it seems that we have the highest growth rate as we would expect, while as we're getting to more mature plots, this seems to be stabilizing. But please keep in mind that those estimates here are only reflecting what we call the above ground biomass growth. So how much the foliage that you see increases or decreases. It is not taking into account at all soil fluxes, because this is an approach that we're currently trying to create and implement in those calculations. Okay, so of course, this is the difference between the gains and the losses. You know, how much trees are increasing and how much carbon or biomass we are losing because trees are dying due to natural dynamics within our plots. So these are the inventory-based methods, and you can understand that you know we have these 15 plots. Other groups have even more, but you know it's very, very difficult to measure almost everything. So we need to find a way to upscale. So one of the techniques, or a suite of techniques that is being used is actually by using satellite-based data flows. So actually what we want here, the basic idea is to create a model, an empirical model, which is useful, or it is generally accurately predict the biomass or the volume of a parcel of land based on some sort of satellite data flows, coupled with topographic or any other source of data that can help the performance of your model. And of course, there are different data flows. There's this optical remote sensing data. Usually, the Sentinel images are quite trendy in the last couple of years. There's this SAR data, and there's this LiDAR data as well. Each of those data flows have its pros and cons, but in general, they are quite useful. And this is in the next slides. I will show you how we try to use them, or at least part of them. So what we did, in addition, and keep in mind trying to upscale to the whole pine forest ecosystem of Lesbos, which is these green areas that you see here, is that we try to to train a model based on satellite data and field-based data, in order every time that the satellite passes and gives us information, to be able to translate what does this mean for the biomass of the pine forest on Lesbos. So what we did is about 80 square plots of about 900 square meters. Within those plots, we identified each of the trees, and we measured a lot of characteristics like the height, the diameter, the crown area, and things like that. We estimated other stand level variables, like how much leaf we have per ground area, or what is the litter biomass, and we create some sort of allometric equations like the ones that you see here. So once we did that, then for the exact same dates, we extracted the information from the satellite, and actually we used both an optical and a LiDAR data flow, and we tried to train those models. I will not, make you feel a bit bored with all these numbers, but more or less, the important bit is that we can more or less estimate various things that relate to the structure of the biomass of our plot with a relatively low, or in some cases higher, accuracy. And these results differ between the data flow of the satellite data that we're using. So it seems that when you are using optical data, this sort of data seems to perform better for the biomass variables, while when you're using LiDAR data, they seem to perform better for stand structure related variables like the number of trees or the mean diameter and things like that. So the general idea here is that we have this model with some intercepts, and this means that every time the satellite passes above our vegetation, above our forest, and give us reliable information, then we can use it to translate this information into biomass. In our case, we want to translate it in biomass. And again, we were actually quite lucky, because we got all this data in 2021, and we trained the model then. We estimated a biomass density across the island, and actually in 2022, we had a big fire at this central southern part of the island. This was the Vatera wildfire that burnt an increased amount of area. And this was of course not nice at all, but for us, it was an opportunity to test how our model works and how this could translate in biomass and differences, and actually in carbon stock differences. So what we did is that using the model that we have trained with data from 2021, we estimated the carbon fluxes in 2022 and 2023. And by doing that, we could go in each of those pixels that we have an estimate of biomass, and keep in mind that those pixels are 10 by 10 meters. And we did the differences. And actually what we saw is that these wildfires led to a reduction of the total carbons, of the mean carbon stock of the island, of about 200 kilograms per square meter. And these are this left tail that you can see in the distribution of the biomass across all those cells that we ran the model and did the prediction. Now, these are the satellite methods that I have been discussing and presenting up to now. There are also the process-based methods. And actually, those methods are based on the development of what we are calling process-based models that simulate the whole dynamics of vegetation, trying to be based on the first principles. So trying to reduce the amount of empiricism or statistical analysis that we include, and trying to actually solve, how photosynthesis is working, how it is being related to how much water you have, or how much nitrogen you have, or how much light you have, and how this is affecting the whole carbon dynamics. Data from inventory or satellite methods that I have been presenting in the previous slides can be used here to either initialize those models, constrain them, or even validate them. The interesting bit with the process-based model is that they cannot be applied from the plot level to the regional scale. And also, and this is quite nice, they have the ability to make longer term, I don't like to say them predictions because they have a high degree of uncertainty, but longer term, at least projections, which we can include different scenarios. So we can include, if we want to say how our forest will be responding by the end of 2100, we can run this type of models and include, for example, climate change scenarios to see, if what we assume that would be a carbon sink will maintain a carbon sink in the future, given the hotter and drier, for example, environment. Of course, those models can be run at very small or larger scales, but in general, what we have been observing is that when you go local scale and you parameterize your models with really local species data, then you get, as you would expect, more accurate predictions. So over the years, this has been started since when I was doing and finishing my PhD. We have developed two kinds of process-based models. The one actually is using annual tree-ring with data, while the second one is really physiological based, so it's actually using photosynthesis to estimate how much carbon you get per leaf, and then you upscale to the tree level, then you upscale to the stand level and at the ecosystem level. And these are parameterized with actual data. And I will be showing some of the results that we have for the Lesbos pine forest based on our physiological, so our second model. So actually, what we could do is that we could run this model along this post-fire chronosequence gradient. And what we see, the results that we see here, is that the amount of carbon that we are capturing seems to be, or the rate by which we are capturing it seems to be higher at mature plots. So it's smaller, then it's increasing up to a point that seems to be higher. Or we can run it along the elevation gradient, and we can see the result from there is more or less, at least for Lesbos, the micro environment, the microclimatic variability does not make a substantial difference for the carbon storage of the plots of the forest. And then we can also apply it, as I told you before, at the island scale. So we can run the model for each one of those small grid cells and estimate, actually, these are estimations, these are mean values for the period 2000-2010, but the estimations are made on a daily basis. So these are the mean values for 3,650 days, actually. And then we can run this with a baseline climate scenario. So under current climate conditions, the assumption that we're doing here is that we have no fire or we have no harvesting. So this is how the whole forest ecosystem across the island of Lesbos performs and how much carbon we think it is capturing. But we can also, as I told you in the beginning, apply those models with different climate change scenarios. And this is where it starts to be quite interesting, because, for example, if you take a medium severity climate change scenario like the RCP 4.5, and you assume here, we make the assumption that we have no fire or harvesting of the forest. What we can see for the carbon balance on the island of Lesbos is that we get a decreasing ability of the stands to capture and store carbon. You see this line going down, which is even worse when you increase the severity of the scenario. So if you go to an extreme 8.5 scenario, you see that in some cases you are almost close to become a source of carbon in the atmosphere. And this is again happening because we have increased respiration rates. So at this temperature, it seems that the rate that the soils are releasing carbon could be at least equivalent to the rate that carbon is being captured from the atmosphere. So I will be quite, I think I was quite quick, but I would like to give some concluding remarks. So if you really plan or you are interested in trying to estimate this carbon storage or these fluxes, there is a range of methods available out there. They can be implemented, you can implement them, but keep in mind that each of those methods has its pros and cons, and it really depends on the level of accuracy that you are requiring or the scale that you want to implement that. Some tips that we have found over the years is that please, when you try to do that, know your species, know how they perform ecologically, ecophysiologically, know your forest, having permanent sites, so places that you keep on monitoring and measuring things can provide quite substantial information. Look also for underground storage. This is not always easy, but it can be done. And try to take into account, if you want to be more realistic, disturbances that could come from fires, for example, or for management. And please remind yourself that, ecosystems provide a range of services, and carbon storage is just one of those. And in some cases, carbon storage is being maximized when other ecosystem services are being protected as well. So that's all from me. And please, if you have any questions, I'm very happy to answer them.